let's take one more look at voltage, work, and potential difference. Now, in order to understand kind of what's going on here, I'm going to go back to the gravitational picture for a minute. Okay, imagine you have a ball resting on the top of a table. Okay, below the table is a chair. Okay, and below the chair and everything is the ground. Okay, so everything's measured here. Now, this ball has some gravitational potential energy. How much gravitational potential energy? Well, we say mgh. Okay, that's fine, but is that h from here to the chair, or is this h from here to here, or is h 0 because it's already resting on the table? Well, the choice is yours. It's ambiguous, okay? So potential energy only has meaning relative to some other point. This has got potential energy relative to the chair. It's got potential energy relative to the floor. It has potential energy relative to the table. But what you pick matters, okay? Now, in electric fields, there's not necessarily a zero that makes sense. Just like here, does it make sense to pick the chair, or does it make sense to pick the table, or does it make sense to pick the floor? You can pick whichever one you want to make the math easier. Well, in electric fields, sometimes it's not really very obvious to figure out what our zero potential is, especially since charges never really get together. Okay, so if I have a big negative charge here, then we know that the electric field is towards it. Okay, now how much work is done if I have a positive charge here and I want to increase its potential energy? Well, if I want to increase its potential energy, I want to make it further away from this negative charge so that it feels like it can fall further. It'll accelerate more towards it, right? Just like if I want to give something more potential energy, I increase its height. Well, it depends on the field strength, and it depends on the size of the charges. And since we don't want the size of this charge to matter, instead of actually measuring electric potential energy, what we measure is electric potential. Okay? And electric potential is voltage, and it's basically joules per coulomb. Okay? Voltage is joules per coulomb, and it describes how much energy is used to move a charge from one point to another in an electric field. Now, if I add work to it, if I add energy to it, I increase the voltage. If the electric field does some work and it wants to pull it in, and so it moves it down, then this thing loses potential energy. Energy is given off. The system does work. Okay, and so what we want to try to figure out is what are our 2 or 3 relationships that we can use to talk about voltage. Well, the first one, okay, is we can say, well, let's just look at electric field. Actually, let's back up one more little step. This is the equation we had last time. Okay, this change in electric potential energy is equal to the work done on a charge, okay, divided by the charge. Okay, and we divide it by the charge because we want it to be independent of however big this is. Okay, it shouldn't matter if it's 3 electrons here, or 300 electrons, or 3 million electrons. Okay, the work done to move more charge is more, but the electric potential between here and here is the same, since we divide by charge, which is why this is a little bit weird. Okay, anyways, we have this one equation, work, we did this yesterday, the change in potential is equal to work divided by charge. Now, if we want, we can take this one step further. If we look at a uniform electric field, which actually isn't uncommon, you get a uniform electric field if you have one charged plate. Okay, and you don't have to have 2, but if you have 2 charged plates, it'll make the field stronger. Okay, and so this side's negative, this side's positive, and of course our field runs from positive to negative. And it's uniform and constant, which means it doesn't matter where I put a charge in here, it's going to feel the same amount of force. So if this is location A and this is location B, the force on charges on each one of these is the same. Okay, so we want to figure out how much work would it take to move a charge from A to B or B to A. Okay, well, then we're actually talking about electric potential again. But remember, work equals force times distance. But force, when it comes to this, is equal to the electric field, okay, the electric field times the charge, Q. force is equal to electric field times charge. That's the force on Q. So if I substitute this into this equation, then I get E times Q times D equals work. But I don't want work, I want potential difference. Well, potential difference is work divided by charge, so I'm going to divide both sides by charge, and I get electric field times distance. So I have two equations that'll tell me how much potential difference, okay, I want to say potential difference in potential energy. It's not quite, because we're dividing by charge. Okay, it's like a difference in potential energy, but it's slightly different since it's independent of the charge it's on. It's like if we were calculating gravitational potential energy, okay, and we were making it independent of mass. A big rock up here and a small rock up here have different potential energies because they have different masses. Okay, but if we divide off the mass, then what we're left with is GH, the strength of the gravitational field, times the distance it is between these 2 points. Okay, well, that's the same thing that's going on over here. Okay, this potential difference is the strength of the field, E, times the distance between those 2 points, A and B. Okay, just like how much energy it actually takes to move the charge is the work done to move the charge divided by the charge. Okay, so these two equations both represent electric potential difference. Okay, and I want to work a couple example problems real quick, and then I'm going to let you guys work a few more. Okay, so the electric field intensity between two plates, it says, is 6,000 newtons per coulomb. Okay, electric field between these two plates, E, is equal to 6,000 newtons per coulomb. And it says the plates are separated by a distance of 0.05 meters. Okay, what is the electric potential difference between them? They're asking what is, basically, if we were going to move a charge from here to here, how much work would that take for every unit of charge we moved? Okay, so they're asking for electric potential difference, which is equal to work per unit charge, which is equal to electric field strength times distance. So we can just take 6,000 times 0.05, which equals 300. Now you're asking yourself, 300 what? Well, electric potential is measured in volts. Okay, but since it's really work divided by charge, this is a joule per coulomb. Okay, a joule per coulomb. We use volts, but it means joules per coulomb. Okay, so that tells me it's going to take 300 joules of work to move every coulomb of charge through this field. Okay, we're going to do a similar problem. Okay, how much work is done when 3 coulombs is moved through an electric potential difference of 1.5 volts? So if I've got an electric potential difference of 1.5 volts, or that tells me it takes 1.5 joules of energy to move every coulomb of charge, and I want to move 3 coulombs of charge, then I'm just going to take this times 3 and I get 4.5. Now what equation am I actually using for that? Well, I'm using the first one, work divided by charge, and I can see 1.5 equals work divided by 3, okay, which equals 4.5 joules. Okay, it takes 4.5 joules of work to move 3 coulombs of charge through this field. Okay, now if the field did work, then the field would do 4.5 joules of work when the charge moved. Okay, now this allows us to do some cool things like figure out the charge to mass ratio of an electron. Okay, one of the cool things, or actually just the charge of an electron, that was done with this is if we had an electric field between these two plates, okay, and we put a charged particle in here, there's forces that act on it. There's its weight, which causes it to fall, mg, and if the field is right, then there's the electric potential here, the force from the electric field pushing it up. And if these two are balanced, we can figure out that this thing's either going to fall at a constant velocity or stay in one spot. If these two things are balanced, then we can say mg equals Fe, and this is actually how a guy named Millikan figured out the charge of an electron. You can read about it in your book on page 573. It's a pretty cool experiment. Okay, but what I want you guys to do today is I want you to work a few practice problems on voltage. Okay, and the problems I want you to take a look at are on page 571, and I want you to look at 17 through 20. Then on page 572, I want you to look at 22 through 25, and one more, actually four more, on page 574. I do want to take a look at 26 through 29. Okay, those are some voltage problems. It's a weird concept because we keep dividing by charge. Instead of just figuring out force times distance's work, we take force times distance divided by charge, and that's electric potential, okay, which we measure in volts, joules per coulomb. Let me know if you have any questions. Good luck.